this is the single line diagram which we are going to talk about today, right? And topic is a real-time case study. So like let's focus on like what are the studies which is needed for this project. So let me quickly give an idea of like what is this single line diagram all about, and then probably I will tell like what are the things which is there inside, and then probably let's go and jump on to the topic and understand like what are the studies we need to perform, why do we need to perform, how to perform, what's that's what we are going to have. So this is a steel industry in one of the famous state in India, Karnataka. This is a steel industry. The steel industry has like rolling mill, electric arc furnace, and ladle refining furnace. 35-ton electric arc furnace, a considerable quantum of the steel industry. 35-ton of ladle refining furnace as well. So the furnace transformer is 20 MVA, which means it's not really small. It's a huge electric arc furnace, and probably 6 MVA LRF transformer and 4 megawatt rolling mill, typically fed from a 110 kV grid via 35/40 MVA transformer. And since electric arc furnace is the harmonic source, there is a harmonic filter which is available, and all the non-linear loads are segregated from other linear loads, so that this harmonics injected by the arc furnace is not really going to affect other loads. So if you understand the process of steel industry predominantly will have like rolling mill, electric arc furnace, and ladle refining furnace. So total load is approximately about like 35 to 40 MVA, which is connected at 33 kV via 35/40 MVA transformer. And since this load is a non-linear load, obviously you need a harmonic filter to suppress the harmonics injected by the electric arc furnace, and there is a harmonic filter as well. So the industry also has some other auxiliaries, DRI1, DRI2, electric arc furnace auxiliaries. It has a cogeneration plant, and the cogeneration plant also has some auxiliaries, and then probably some oxygen plant motor, some other auxiliary loads. So means all small auxiliary loads are fed from 4 which are fed from 415 volt transformer. Only one motor, which is 750 kilowatt motor at oxygen plant, which is directly fed from 11 kV. Since the industry, like a steel industry, the predominant process is converting the electricity to heat, and as per thermodynamics law, which we know, converting the electricity to heat or heat to the electricity is very inefficient process. And probably this industry has to pay a huge electricity bill to the utility. They thought of putting up a cogeneration plant, which is 35 megawatt turbine generator. And this can be called as CPP, captive power plant, right? Or cogeneration, whatever it is. So like anyway, you need a heat for your process industry, which is steel industry in this case. And like when you are trying to convert the electricity into heat, your efficiency will be less than 40%. Similarly, when you try to convert the heat into electricity, the efficiency is again less than 40%. That's the reason why typically all our thermal power plants have efficiency of less than 40%. Even ultra critical, super critical thermal plants have an efficiency of in the range of only 35%. So here this process industry tries to use both heat as well as electricity, which means they will use coal, burn the coal to generate steam, and they try to use to generate the power, and that efficiency is in the range of about 30 to 32%, which means we couldn't convert the entire chemical energy of the coal into heat, then into electricity. Out of like 100 kilojoules or kilocalories per second or a minute what I am dumping inside the coal bunker, I am getting only 35% or 32% as an electricity. Remaining predominantly is wasted as a heat. That heat could be used for a process. So you can, try in cogeneration both the options. You can generate electricity first, then probably the excess heat you can use it for a process, or you can use the heat for the process first, then the wastage of heat you can use to generate a steam, then to power. So if you do generate the electricity first, then use it for a process, that's called a top cycle with respect to cogeneration plant. And if you use it for a process, and then probably the wastage heat, like waste heat recovery, if you're using it for steam generation and then generation, that is called the bottom cycle. So here, like they are using 35 megawatt turbine generator, right? So if you look at this industry, so means what say it is 35/40 MVA stepping down from 110 bar 11 kV, 110 bar 11 kV and feeding the loads, the 110 bar 33 kV feeding the critical nonlinear loads, electric arc furnace, ladle refining furnace and rolling mill 3 kV and other auxiliary loads at 11 kV, oxygen plant motor directly at 11 kV, all other remaining loads at 415 volt. It has cogeneration plant of 35 megawatt, and of course that generation has some auxiliaries like boiler, feed pump, right? CCP, IAPA, like some auxiliary loads. That's all met at 6.6 kV. And this industry is connected at 110 kV. There is a double circuit 3 kilometer overhead line takes this to the nearby substation. From there, as a single circuit 12 kilometer line takes to another 110 kV substation, where which is like 220 bar 110 kV substation, which is an existing substation which is available. All right, now let's go and probably ask from a pure power system study engineer perspective. I am a power system engineer. Means so this is a task which is given to me. Like, what are the studies which you propose as a power system study engineer? Like, you are seeing like you are getting a power supply 220 kV grid, stepping down to 110 kV via two numbers of 100 MVA transformer, 12 kilometer single circuit, 3 kilometer double circuit, main and transfer bus, 33 kV step down, feeding critical arc furnace loads along with the harmonic filter, stepping down to 11 kV, feeding oxygen motor, and then probably stepping down to 415 and loading 35 megawatt cogeneration plant, generating at 11 kV, stepping to 110 kV directly, and probably there is an auxiliary transformer which is stepping down from 11 kV to 6.3 kV. From power system studies perspective, what are the parameters to be optimized? What are the studies which you need? So obvious, you need to perform load flow studies, you need to perform a short circuit study, and you have a motor. Obvious, you have to perform motor starting study or motor acceleration study. You need to perform a transient stability to find out the critical clearing time because you have a cogenerations. You need to perform grid islanding and load setting studies because there is a probable option that you connect it to the grid and you disconnect it from the grid and you operate. You need to perform definitely a harmonic analysis because you have an arc furnace and you have to size the filter. You need to perform a relay coordination. You need to perform maybe an arc flash studies. Needless to say, you have to perform an earthing studies for 110 kV yard, and probably means in case if required, you need to perform insulation coordination study. May not be really mandatory, but you can, if probably the length between the switch yard and the transformer is more and stuff, then you need to perform insulation coordination study. If you're a power system engineer, like you need to really look at all these 10 studies to optimize your system. If you want to look at the system, you need to perform all the studies, and probably that's most key challenge which I am looking at. So probably we should not really do the study just because we have to do the study. We should have a clear agenda, a clear objective behind why we are performing a study. What I mean by that, before performing a load flow, I need to know what are my objectives, what are my constraints, what parameter to be optimized. If you keep these three things in clear, then probably I guess like your entire problem will be solved. So when before doing any studies, ask yourself a question: what's the objective of the study? What are the constraints? And the last one, what parameter to be optimized? If you ask all these three questions, and if you have a crystal clear answer for all these three questions, then probably our task is quite simple. I guess like time may not allow us to go through the objective constraints and what parameters to be optimized for all studies, but at least try our level best to put up the subjective constraints, what parameter to be optimized, at least for a load flow. What's the objective of load flow? Let's take only load flow, not really anything else. Specific to this project, why do we need to perform load flow? What's the objective of performing load flow? Okay, rather than saying probably let me come from what are the parameters to be optimized. Let me start from there. OLTC or DETC for generator transformer, arc furnace transformer, means for say 110 bar 11 kV power transformer and unit auxiliary transformer. We need to decide whether OLTC is needed, this transformers, or de-energized tap changer is sufficient. That's pretty much what we need to, that's what pretty much we need to do, or we need to understand. For this 40 MVA auxiliary arc furnace transformer, 15 MVA auxiliary transformer, the 45 MVA generator step up transformer, 6.3 unit auxiliary transformer for this power plant, whether this transformers has to be on-load tap changes or de-energized tap changes. If it is OLTC, what should be the range? Do we need a power factor correction capacitor? If so, how much rating of the capacitor? What should be the generator terminal set point voltage? Generator terminal set point voltage is going to play a very, very critical role in deciding what's the reactive power which it injects to the system, and what's the power factor which is maintained at the point of common coupling. What's the means for say whether generator step up transformer capable of extracting the entire capability curve of the generator. So these are all probably the parameters to be optimized. So you need to decide whether OLTC is needed or de-energized tap changer is sufficient. If you need on-load tap changer, what's the range? And do we need a correction capacity? If so, what's the rating of it? Can I adjust the generator terminal set point voltage and optimize the capacitor bank or eliminate the capacitor bank? So what's the role of generator terminal set point voltage in maintaining the power factor at the point of coupling? Whether the generator transformer, its impedance and OLTC, whether this is capable of extracting the entire capability curve of the generator transformer impedance. What's the transformer impedance of generator step up transformer, this transformers, etc., etc. Of course, load flow alone may not be able to optimize it, but like load flow is a key criteria. Load flow, short circuit, and motor starting together has to evaluate what's the impedance of the transformer. So these are all the points probably which we need to really look at. What are the parameters to be optimized? And if we have that agenda or that objective is clear, like what parameter to be optimized, then like I mean to say we will seek the right information. We will seek the right information from the customer to optimize it. And when you do a project at the beginning, in the planning stage, when the steel industry is expected to come probably 1 year down the line, 2 years down the line, you do not know the loads. Mechanical engineer has to freeze the predominant loads. So it is always a debate like how to optimize it from pure electrical perspective. So at least from our perspective, with whatever may be the assumptions which is available from the mechanical team or from other teams, you should clear-cutly decide what's the parameter to be optimized. And of course, what parameter to be optimized, needless to say, cost is always the king, or price or money is always the king, right? So that needless to say, cost to be optimized. And when we say cost to be optimized, like there is other probably a debate which always comes into our mind. Whether capital cost has to be optimized, running cost has to be optimized, and how to treat this capital investment versus running cost, right? So you need to be probably look at from many other perspectives also. And like it is just not about like the design phase, and the operational phase also probably means what to say, gives some idea, some thoughts for getting optimized cost in the running. Let me say a typical example. Here you can see this is 35 megawatt generator, and you have like 40 MVA and 15 MVA. And if you look at loads like here 26 and probably it's like a 4 rolling mill, which what we have seen, right? Like predominantly about 27-28 megawatt load, and here like about 6-7 megawatt load, right? There is a probability then when the electric arc furnace is not running, you have sufficient capacity to export the power to the grid. But like when you're exporting the power, what's the price electricity board which pays to this industry is the question to be asked. Assume that like they are paying, say example, $0.1, 100 cents, which they are paying per unit electricity. and cost of generation from this is, say example, 120 cents or 130 cents, and it is not logical to probably generate a power and pump the power to the grid, right? So you need to understand, means also the optimization is from one perspective on the engineering stage, and the second optimization probably has to happen along the course or along the operation of that one. And like objective of our custom studies, we are limiting it to only the design engineering phase, not really the operational phase. Operational phase or like power management spectrum, which we are probably keeping it aside. Let's try to focus pure on the design phase. All right, let's probably go a bit more and ask, like, what are the constraints? OLTC range could be a constraint. Generator Qmin, Qmax could be a constraint. Even if you have an automatic power factor correction capacitor at low voltage systems, that step could be a constraint. Load which is fluctuating could be a constraint. Grid voltage fluctuation could be a constraint. What's the power factor which you need to maintain at grid might be a constraint. Contract demand, essentially you cannot exceed, otherwise like you will be having a problem of like huge penalty. Contract demand could be a constraint. So means what you need to say, when you are trying to optimize something, you need to ensure that you are optimizing something with some constraints. You cannot optimize something without any constraints, right? Like optimization problems along with the constraints are quite natural phenomena. You can optimize only when you have a constraint, otherwise there is no point in optimizing it. Double bus bar scheme is missing in ETAP model, and that's the objective of load flow. Load flow, probably if it is these are all the objectives, whether it is a single bus bar with a section main and transfer, or two main or 1.5 breaker scheme, all are immaterial for a load flow analysis. That's the real reason why main and transfer scheme, which has been probably there in the normal SLT, which is not really modeled in ETAP SLT. It's a main and transfer, right? It is not really adding any value in the load flow. So this could be as simplified as this. So this is really an important aspect. Like what is to be optimized, for that like you need to model it in detail. When like your optimization parameter is something beyond, and for that like detailed modeling of like double bus bar or main and transfer, 1.5 breaker scheme, whatever the breaker scheme or whatever may be the substation scheme here, it's not really going to have any impact on load flow. So there is no point in modeling it. All right, let's probably go and ask maybe few more questions. Then like what's the objective? IEEE 399 talks beautifully about it. Like what's the objective of load flow? And what's the objective of load flow? You need to, of course, you need to, look at from the perspective of IEEE 399 with respect to what is applicable for your project, right? Like IEEE 399 gives the generic guideline. You need to probably optimize from your own perspective. Let me bring quickly IEEE 399 and the relevant page. This is IEEE 399 chapter 6 load flow, and probably the first paragraph of it, right? They beautifully define it, like what's the objective. You need to find out the component loading or a circuit loading. Of course, you need to find out what's the equipment loading of all branches. It could include transformers, cables, transmission lines, etc. So that's the first objective, and you need to ensure that like what is the percentage loading of the transformer, what is the percentage loading of the cable, what is the available transfer capacity ATC which is available in the transmission lines for a future use. So that's another important aspect, I guess, like most of the times, which is in fact missed. When we have something like this, what's the available transfer capacity which is available between this 110 kV substation to this 110 kV substation in the length of about 12 kilometers is an essential outcome from a load flow analysis, which gives an idea in the future if some other industry asks the connection or connectivity at this place, up to what extent this utility can extend, right? So that's from other perspective which we need to really look at. And coming back to this, of course, you need to have like steady state bus voltage, and probably means we have not really added some constraints. Definitely voltage is a constraint. What's the acceptable voltage range? Plus or minus 10%, plus or minus 5%. That's a constraint. You cannot optimize the loss by increasing the voltage by 150%. The maximum voltage plus 5% or plus 10%, that is a constraint. Say example, if your objective is to minimize the loss, you need to maintain the voltage well within the acceptable limit. You need to maintain the contract demand within the acceptable limit. You have to obey the export limits. What I mean by that? So contract demand, what is the maximum import which you can do it from the utility? Export constraints, what's the maximum power which you can inject back to the grid? And what is the power factor to be maintained at the grid? What's the grid voltage, right? And the load changes. All these things are constraints, and you need to optimize your parameters. Optimize your equipments, their ratings, their data sheets before procuring these equipments. That's the real reason why this load flow is needed at the planning stage, not really after construction of this industry. 90% of the cases, we do load flow analysis for the sake of documentation at the verge of completion of the project or before handing it over to the customer. There is no point in probably performing the load flow analysis when everything is constructed and you are trying to hand it over to the customer from an EPC perspective. Engineering procurement contractor has to perform load flow or a short circuit at the beginning of the projects to optimize some parameters. Then probably you need to go to like what are the cases which you need to perform. So I'm not really sure like how many cases which you frame for this study. Like when you're performing only load flow, you can perform like multiple cases with the grid voltage, with the load, with the generator available, not available, etc. Right? 100% grid voltage, 105% grid voltage, 95% grid voltage. Load is maximum load, minimum load. Generator is available, not available. It's generating 35 megawatt, 28 megawatt, 10 megawatt. When the grid is available, grid is not available, right? So you can have like multiple cases. And all this probable combination which you need to run before deciding OLTC range, impedance, and probably means for say voltage, tolerance, power factor corrections, all these things. By means of running a load flow for a single case, you cannot conclude something is enough or something is not enough, which is another important aspect. So means before you are deciding a power factor correction capacitor, you need to look at like all possible combinations. What I mean by that? Shall we conclude that like this much capacitor is sufficient by means of running only one load flow case? Answer is essentially no. Why? Probably, so say power system is the most dynamic system in the world. And load flow is a steady state analysis. Let me repeat my statement. Power system is the most dynamic system in the world because electricity is the only product which cannot be stored, at least economically. Electricity is the only product which cannot be stored, which means the electricity generated has to be consumed at the same moment, same seconds, same milliseconds. If the electricity is more than the generation, then the frequency will fall. And power system is the most dynamic system. And the beauty is we are trying to identify that most dynamic system in the world using a steady state analysis, fixing all the parameters, running only one simple case. So what I mean, when you are trying to optimize something, it is absolutely okay to optimize something with a load flow analysis. Ensure you are framing the load flow cases, including all the worst case possible scenarios, so that what are the parameter which you have designed will withstand its lifetime, typically about at least 25 years, without any constraints. If you have decided your equipment parameter by means of only one case or a two case, that's not the only case which is going to come for your system. Till the 25 years of the life of this equipment which you have designed. Like maybe I can add up maybe only one more video to you to probably talk more with respect to the more with respect to the I mean, it's talking about power systems, most dynamic, steady state, all these things, etc., etc. I strongly recommend this video. That was our probably first YouTube live. Indian grid stability, where I have probably gone depth and probably step by step of like how to assess the power system, the most dynamic system in the world, by using a steady state analysis, as well as probably a little bit of dynamics. The same system we have done probably load flow for all this possible different combinations. And the first step we have done, what are the informations which has to be collected for a grid, a transformer, transmission lines, cables, motors, generators, loads, capacitors. What are the informations like input data required to be collected, and what are the cases to be framed? What are the cases to be framed? What are the cases to be framed? We frame the cases, and then probably, I mean, what say, this is the outcome of it. And probably you can see here, like CPP alone, grid alone, normal, like there could be like multiple cases which is possible. When we say CPP alone, only CPP is available, the grid is off. When we say only grid alone, grid is on, like the generator is off. And then probably means for say when normal mode, like both are on. And probably means for say all these possible combinations, we have fixed it as a scenario. And like we have phrased all this possible configurations, and probably able to optimize this in a single click, even irrespective of the parameter change in the future, using the study wizard, right? Like single click, all the cases which you have framed probably will run and gives the results. Hope you can change, look at like here, it's on and off and on and off and stuff like that. And all the results will be available in a single Excel in the prescribed format which you want, so that you can take out the results in an Excel and you can optimize it and you can go ahead with the report. So this is a case study which we have done, and the course is available in Zenler, and this is a course. It's like this is a course. So what are the things which we have done? Like we have done a detailed introduction of the system, objective of the load flow. We have framed the input requirements along the session, the same Excel of grid, transformer, transmission line, like what are the information which is needed for this to optimize our system. Then like modeling in ETAP, framing the different cases and the simulations. That's where we have framed about like this 15 cases. And then like running the simulation and probably making the inferences, results analysis, and some automation in the ETAP. And probably you can look at like what are the available nodes, ETAP SLT, input Excel, what you are seeing now. Nodes, what's the nodes which we have taken across these 3 sessions, and the ETAP simulation file to just cross verify it. This SLT has been developed and modeled in probably about like 45 minutes in that session. So you can understand how to develop such a single line diagram in 45 minutes. And then probably means what say, what are the standard transmission line conductors and how to choose the voltage, why this industry is decided to connect it at 110 kV, why not 220 kV, why not 66 kV, why not 33 kV, etc., which we have asked. Thanks for joining. We will meet again. Have a fantastic day ahead. Take care. Bye bye.